In our first video from Chapter 3, Introducing Multiple Regression, we talked about t-test, r-squared, and adjusted r-squared values. In this video, we're going to discuss how to determine which variables to use in a multiple regression analysis. We will be using the cars dataset from Chapter 3, and our goal is to build a multiple regression model to predict the price of cars. As we showed earlier, when we used mileage to predict the price of cars, we found an r-squared of only 2%. However, if you look at our dataset, there are many other quantitative variables we can choose from. If we include all of these variables into one regression model, we find that our r-squared value has jumped from just 2% to 44.6%. That's quite a bit better. But do we really need all 7 terms or all 7 explanatory variables in our model? Could just 1 or 2 or maybe 3 or 4 of these variables give us a model that works just as well as one that has all 7 terms? Our first approach to answering this question is to use step-forward regression, sometimes called forward selection. In this process, we first ask the question, which single explanatory variable best predicts price? And so what we do is we create every single simple linear regression model using one explanatory variable and the response price. If we use the variable cruise to predict price, we have an r-squared of 18.56%, much better than the r-squared of 2% that came from mileage. Notice that cruise only has 2 levels. It's either 0, meaning it doesn't have cruise control, or it's 1, where it does have cruise control. Even though a linear regression model may not be the best way to evaluate cruise, we see that it can be used to predict price better than mileage can. The next simple linear regression model that we try is cylinder, which gives us an r-squared of 32.39%. We then try mileage, and as we saw before, the r-squared is only 2%. If we use liter, we get an r-squared of 31%. We continue this process for all our explanatory variables, and we find the model with the best r-squared value. And here, that model is the one using cylinder as the explanatory variable with an r-squared of 32.39. Even though the model including cylinder has the best r-squared, it's important to note the model that uses liter is a very close second. The second step in step-forward regression is to find the best 2-variable model to predict price. Since cylinder was determined to be the best single-variable model, we will always include cylinder and try cylinder with the other variables in our model. For example, if we try the model with cylinder and cruise, we get an r-squared of 38.4% and an adjusted r-squared of 38.2. So in essence, what this model is doing is using both cylinder and cruise to predict price. And if we look at this graphic, we see that if we use 0 for cruise and 4 for cylinder, we can predict the price of the car. We continue trying models. For example, if we use cylinder and mileage, we obtain an r-squared of 34% and an adjusted r-squared value of 33.8. Here we test the model with cylinder and liter as explanatory variables. Notice that the r-squared here improves only slightly. After calculating the r-squared values for every model with 2 terms, where one of them is cylinder, we find that the best model in terms of r-squared or adjusted r-squared is the one using cylinder and cruise. So the third step in step-forward regression is to do the same process where we try 3-variable models. Trying all models that include both cylinder and cruise, we find that leather has the biggest impact on r-squared, giving us an r-squared of 40.4 and adjusted r-squared of 40.2. We repeat this process again using cylinder, cruise, and leather, and then find the 4th term to add. We find adding the term mileage to our model increases our r-squared from 40.4 to 42.3. This model has the highest r-squared value with 4 terms under the condition that cylinder, cruise, and leather must be in the model. Repeating this process again, keeping cylinder, cruise, leather, and mileage in our model, we find that doors is the next variable that best improves our r-squared value. Repeating the process again, we then add sound. If you use a statistical software package to calculate step-forward regression, this is the model that you will be given. You notice that there's one term in this model that's not included, and that's liter. The reason the full model is not suggested is you notice that adding the term leader did not improve the R-squared value, and in fact the adjusted R-squared went down a little bit. Most statistical software packages conduct a hypothesis test to see if the R-squared value significantly improves enough to add those terms. When the R-squared value isn't improving enough, it will decide to stop and not add any more terms to the model. So in terms of R-squared or adjusted R-squared values, adding leader really is not that helpful in the regression model. However, it's important to recognize when we first ran the initial regression models with just one term, leader was an important variable. As we see here, the R-squared for leader is almost as good as cylinder. However, the output for stepwise regression in most statistical software packages will not give any indication that leader could be a valuable predictor of price. Similar to step-forward regression, we can do step-backwards regression, and that's using a very similar process, but instead of starting out with just one term, we start with every term in our model. Here we have all 7 variables, and we determine which single variable can we remove without significantly lowering the R-squared or the adjusted R-squared values. The step-backward procedure stopped here because it determined there were no other terms that could be removed and still maintain a similar R-squared value. In addition to step-forward and step-backward regression, there are bidirectional stepwise procedures that use a combination of both step-forward and step-backward to determine the best model. While the step-forward and step-backward regression techniques described in this video used R-squared and adjusted R-squared, there are several other criterion that can be used to determine the best model. For example, a Keki's information criterion, Bayesian information criterion, and Mallow-CCP. Sequential techniques, such as the ones I've described here, have a tendency to include too many variables and at the same time eliminate important variables. You notice that both step-forward and step-backward regression models eliminated leader and gave the user no indication that leader could be an important variable. With improvements in technology, most statisticians prefer to use more global techniques, such as best subsets models, which compares all possible subsets of the explanatory variables. Here's the output of best subsets regression using the same CARS data set. Notice it lists the number of variables in the model, the R-squared value, the adjusted R-squared value, Mallow-CCP, the standard error, and then the explanatory variables. In this output, we see that cylinder is suggested as the best single variable model. It has the highest R-squared. But in this output, the user can see that leader is also a good predictor in terms of R-squared. It shows us that the best two-term model is cylinder and cruise, but the second best model to predict price is using leader and cruise control. This option wasn't even considered in stepwise regression. As we work down the list, we see that our adjusted R-squared continues to improve until we hit 6 terms in our model. When we hit our 7th term, the R-squared adjusted goes down. With this information from best subsets regression, a statistician can use the adjusted R-squared value to determine that this 6-variable model is likely the best model to use. However, in best subsets regression, this output also shows the statistician that maybe leader should be considered as well. This leads me to conclude that I should look at residual plots very carefully, including residual plots for models with leader, to determine what is my best overall model. Even though I now have a suggested model, I should not use that model without first looking at residual plots. So it's important to recognize that stepwise regression techniques can often ignore very important explanatory variables. The output in stepwise regression would give the user no indication that leader was important. Best subsets or other global techniques are often preferable to stepwise regression techniques. Both best subsets and stepwise regression methods only consider linear relationships between the response and the explanatory variables. For example, there might be a strong quadratic relationship between one of the x variables and the response variable. Only looking at residual plots would help us identify that a quadratic term should be included. In essence, none of these variable selection techniques should be done without looking at residual plots. Residual graphs are essential in validating whether the model is appropriate. Through looking at these residual plots, we could identify whether transformations, interactions, or quadratic terms may improve the model. Often they do, but we wouldn't know that unless we look at the residual plots. For example, our textbook describes how the residual plots demonstrate that a transformation is needed in our car's data. And as we describe in our next video, whenever these variable selection techniques are used, the p-value corresponding to the significance of each individual coefficient are not very reliable. When you're conducting multiple regression, variable selection techniques can be very useful. However, it's important to recognize that a statistician must also look carefully at the residual plots and understand the output of these stepwise procedures in order to use them correctly.